Hello, December 27th, 2024. So we've come to problem 7. The constant terms we already solved in problem 1. F vanishes and EK halves gives unity. So we just need to write the sum. And now I do it from we'll better write a set here. Zeta of 1 minus 2 lambda EK halves of Z plus something, zeta of 1 minus 2 lambda times some constant beta from the book, F. I believe that's the constant term. Actually, we should... No, I can't. I think we should be able to compute it explicitly, but I can't do that. Next, the coefficient of the first power. So that was question A and B. That's C1 it's called. And it should be L of chi minus 1 to lambda at, shouldn't it be 1 minus lambda? I don't recall that, I'll just have to look it up. Yeah, I think that's what it is. So my idea when I read the problem was can we compute this explicitly? In terms of the zeta function, I mean. Now, if lambda is even, then it's just the unit character, so we can disregard it. And then 1 minus, we'll have it, yeah. 1 minus lambda. And we can't do that, but we can do it, compute the 1 of lambda. And I believe that's just the zeta function of lambda. And we know that from even lambda, and I really can't remember the formula. I'll just find it. And then for lambda odd, we can just look at that before I take a little break. And again, we can write up of lambda, and then use the inversion formula for the L series. I don't really know if we've had this before. My first idea was to split it, n being equivalent to 1 modulo 4, and then, so let's just write it up what I meant. So we first take 4n plus 1 minus lambda minus 4n minus 1 to minus lambda. And here we sum from n is 0 to infinity, and here from n is 1 to infinity. I don't know if this helps anything. It's sums we have had to handle before, but I don't recall what to do. In the next problems, I think we need to consider lambda equals 2, meaning this is the important case, where I think it's easy to find it. Okay, so the plan is that I find this and then see if there's any future to this, and then I shall return. It turns out that I solved the problem, I think, but I didn't turn on the recording. So I talked for 5 minutes or something, maybe 10, and think I've solved the problem. And now I'll have to tell you what I did. To find this, we must use this, and then the formula here to express zeta in 1 minus s, or 1 minus lambda, in terms of theta of lambda. And in chapter 2, this function was proven to be symmetric around s equals 1/2. The vertical line s equals, or the real part of s equals 1/2. And I use that to isolate zeta of 1 minus s. This can be reduced, and actually Mabel could do that, assuming s is positive and even. I'm a little surprised it could do that. I can't make it expand the zeta function itself in terms of Bernoulli numbers, but maybe Mabel thinks this is more succinct than a long expression with Bernoulli numbers, and actually so do I. Now, it was able to reduce it to this, surprise. So what it had to do is first to extend by gamma of 1/2 plus s halves, and then use the formula for gamma of one number times gamma of 1/2 plus that number, which gives this and some more fractions, some more stuff. Now I copied it over here. And then I use the value of the zeta function, and this gives this. First, 2 to lambda minus 1 cancels. Pi to lambda cancels. I to lambda cancels. Most of the lambdas here cancel. So we end up with this. So that's my value when lambda is even. And when lambda is odd, I first noticed that I failed to sum over the even integers here. But it really doesn't matter, because it occurred to me at this point that when lambda is when lambda is odd, then this is chi minus 1. And minus 1 is equivalent to 3 modulo 4. And we proved, I guess, in the last problem that in that case, BL vanishes. When L is equivalent to 3 modulo 4, then BL vanishes. So this is a case where B1 vanishes. So we don't have to compute it in its own right. And that turned out to be all we had to say about this. So sorry you didn't see me do it, but